welcome to this video as we continue our journey on transformations. Our main learning intention from this is to be able to use transformations to help us when we're sketching. To be successful at this is to sketch a transform graph when we know what its basic function looks like. And for example, is be able to sketch the graph of y equals 4 on x plus 5 minus 3. Looks slightly complex, but we can recognize that this is just a modified or transformed form of y equals 1 on x. So if we know that, we know what that looks like, and that's a hyperbola. We can then just think of it as a transformed hyperbola. Is it transformations, reflections, or dilations? When we talk about common functions, we're talking about quadratics, cubics, hyperbolas, truncus, square root graphs, and possibly circle graphs. They're the main ones what we consider common functions at a Year 12 level. So let's get going into it. So we're going to use the information we've learned about transformations, and hopefully we're at the point where inspection is really starting to click and we can recognize the transformations just by looking at the transition. But a common square root graph starts at 0, 0. And then goes up like that, and then I'm going to put in a point of reference and call that point there. If I put 1 in as x, put it in, square root of 1 is just 1. And so I have the intercepts taken as 0, 0, and then it goes through 1, 1, and then keeps going on and on and on. Now, sketch the graph of y equals negative square root of x minus 1. Hopefully we recognize, that is a translation. We have moved 1 unit to the right. Okay, so everything will have moved 1 unit to the right, and then we also notice we have the negative at the front. You might not recognize that so much quickly, but what I think of is that every function or equation is a process, a machine. Yeah, put something in, do something to it, get out. We're putting in our sense, an x coordinate, doing some stuff to it, we get out a y coordinate. Let's think what that negative does to whatever we've done. We've put in our x, maybe we get 2 out. It now becomes negative 2. So every value that we're putting in that was getting a positive y value, that's now negative. That means it's flipped down. So if we see this negative out the front, we can tell that that is reflected about the x-axis. So we know in our case the dot's moved over. Instead of being at 0, 0, we're now at 1, 0, and instead of being up that way, we are now actually reflected this way. And instead of this point being at 1, what we would think, it's down and underneath, but it's also pushed across 1, so we're now at 2, negative 1. So that comes from recognizing the transformations and also knowing what the basic shape is. We sketched the graph as it says there on the previous slide. We sketched the graph as we functionally knew it, and then we applied some transformations to it. So what were the transformations? We first moved across to the right, which would look like that, which would put us at 2, 1. Okay? And then we have reflected. So 1 we moved across, and then step 2 we reflected. And now we've got our new graph. And if we think of doing those things to the shape, then we can break down a problem like it shows down here, that y equals 4 on x plus 5 minus 3 starts as a y equals 1 on x, which is here. We then dilate from the x-axis, so we're stretching the graph up away from the x-axis. So that point 1, 1 now becomes 1, 4 because we've dilated by a factor of 4. We then translated in the negative direction of the x-axis. We see the plus x plus 5. We know that's actually a negative translation along the x-axis. We've gone 5 units. Everything is being moved 5 units that way. And then lastly, we have a negative direction of the y-axis. We've gone down -3, so all coordinates have then moved down 3 units. So if you know some initial coordinate points, you can apply all those transformations and get there. The textbook suggests that you try this a few times, is start with the starting sketch, draw the first transformation, then apply the second transformation. So you're going to end up doing 4 sketches. But we want to, especially in the exam, there's never going to be a requirement to draw each individual transformation. It'll say, here's your initial graph, here's the final, or it'll just give you the final one, sketch it. So how can we shortcut all the way across? How can we be more efficient? And that comes down to us recognizing the H and K values. We've talked about before in class. There was 1 or 2 of you away in this class when I went over this, but this is what we call the general or standard forms of the equations, and my kitten is back over there just making some noise. These are the general forms of the equation where, and I haven't filled in the square root version, is y equals a square root x minus h plus k outside of the square root, where if we can recognize or get the equation written in this form, we can straight away see our h and k, which are our horizontal and vertical translations. So if we can read the h value, we instantly know for the quadratic, that's called the turning point. For a cubic of this form, that's called the point of inflection. We know where that is. We know where the starting point of the square root is. In hyperbolas, we can see what the vertical asymptote and horizontal asymptotes are, same with the truncus. And then for a circle, we can see where the center of the circle is and what its radius is, if we can recognize in those forms. There was all that homework on the Google Classroom for practicing these skills of just recognizing the H and K values. If you haven't done it, I highly suggest you do it. But, so we can use this. We can use the H and K. We'll use that as our basis. If we can straight away find either the turning point or the point of inflection, the starting point or the asymptotes, that's 90% of the problem done. You know where the rest of the graph is going to be around those points. We just got to get the correct H and K. Let's go back to the slides. Okay. Now the hint for getting the correct H and K is whenever it's written in the form like it is there on the slide, you can read it straight off. Unless, okay, so we can read H and K, okay, we can read it straight away unless, and this is a big unless, okay, X is negative itself, so the actual X may have a negative there, or X has a coefficient. Okay, and in both those cases, you have to take that out as a common factor first to read the correct H value. It rarely ever impacts the K, but it'll definitely impact the H value. So I know this isn't the question on the slide, but for example, if we had y equals 1 on 2x plus 3, okay, you actually, since this x has a coefficient, you need to take that as a common factor in that denominator. And so we want to get y equals 1 on 2. We take it as a common factor. We need to take it out of the 3 as a common factor, so we get plus 3 on 2. Now we can actually read the correct H value. Same thing for y equals 1 on, it might be negative x plus 3 all squared. You need, since that x has a negative, we need to take it out as a common factor, so we get 1 on negative bracket x minus 3 all squared. Now we can read the correct H value again. The x having coefficient or being negative, we need to recognize that what I'm saying by that is the very directly applied to the x. If we had y equals negative 1 on x minus 2 all squared, well, yes, there is a negative here, but that's not the x itself. It's part of the whole function, so you don't need to worry about taking that out as a common factor. You could read, in this case, you can read straight away, well, in this case, my h is 2. It doesn't impact it. So that's just a really clear point I want to make. To work most efficiently is let's identify the h value, let's identify the k value. As soon as you have those, you can plot either your starting point, turning point, or asymptotes, and then from there, all you need to do is calculate the intercepts, which you're going to have to do anyway. Even if you do the fancy step by step transformation, you're still going to have to calculate. You're going to have to perform mathematics. Okay, subbing in y equals 0, x equals 0 to find that intercept there and that intercept there. You're still going to have to do that. So we may as well work efficiently and get the asymptotes or turning points really quickly. So let's jump into this one. Straight away, I can see from this we have y equals 2 on x minus 1 all squared minus 2. I recognize straight away that this is a truncus, okay, which is what? Y equals 1 on x squared. It's a transformed version of a truncus. From that, going back to this, and if you don't have this, pause the video and write all this down, okay, and pay careful attention that it's x minus h, x minus h, x minus h everywhere, but it's plus k's. So you have to swap the sign on the h value. There. Okay, so straight away off this, that's my h value in there with the x, and that's my k value there. I get h is equal to 1 and k is equal to negative 2. Okay, so I go down to h is 1 there, that's x equals 1. That's going to be my vertical asymptote, x equals 1. Straight away, I also get my horizontal asymptote, which is y is equal to negative 2. So from these we can say, oh, that's x equals 1 instead. And this is y equals negative 2. I get my asymptotes. We know then, and I'm going to put in a line like that. We know it's going to have some shape like this, but I would suggest you could put that in grey lead first, but we want to find out what the intercepts are so we can accurately draw this. So that's getting a rough idea of the shape. Now we need to get our intercepts. And to do that, we just let x equals 0 and then y equals 0. So first off, I'm going to let y equal to 0. So I get 0 is equal to 2 on x minus 1 all squared minus 2. I get 2 equal to 2 on x minus 1 all squared. Divide both sides by 2 to get rid of the 2 in the numerator. So I end up with 1 is equal to 1 on x minus 1 all squared. I end up with x minus 1 all squared is equal to 1. Take the square root of both sides, I get x minus 1 is equal to, and if I take the square root of that side and I take the square root of that side, I now get square root of 1 is equal to plus or minus 1. When we take the square root of anything, we need to recognize that there's a plus or negative solution to that, and then I get x is equal to plus or minus 1 plus 1. So if I read that as plus 1, what I'm looking at is plus or minus. If I read that as the plus, I get that as equal to 1 plus 1, which is 2. Or if I read it as negative, I get negative 1 plus 1 is 0. So let's delete that line and delete that line. I can say straight away, well, there's one asymptote at 2, 0, and I also get, that was that one. I might put it in green just to be clear. There's 2, 0, and my other asymptote is 0, 0. Now my intercepts when y equals 0. We can also do let x equals 0. I'm going to put this in. I recognize straight away, oh, that is also, this 0, 0 point is not only my x-intercept, it's also my y-intercept. But just to show you the process to find the y-intercept, we let x equal 0. We get y is equal to 2 on 0 minus 1, all squared minus 2. We get y is equal to 2 on negative 1 all squared is 1 minus 2. So we get is equal to 2, take 2 is equal to 0. So we get that 0, 0 again, which is there. So I can now draw my truncus in. Directly through the intercepts. That's it for the video. So the big takeaway from this is to do any of the sketching problems we're going to have on the exam, to do them efficiently, we need to be able to find the H and K values first, which we read off by recognizing equations when they're in standard form. The only issue we ever come across is when the X itself, okay, directly has a coefficient or is negative. And in those cases, you must take that coefficient or negative out to get the correct H and to get the correct H value. I'll leave it there. I'll see you in class.